Our final presenter for today is Dr. Margaret Martonosi, who is Assistant Director for Computer and Information Science and Engineering at the National Science Foundation. In this role, she is responsible for leading the CISE mission to uphold the nation's leadership in scientific discovery and engineering innovation through its support of fundamental research and education in computer and information science and engineering, as well as transformative advances in research cyber infrastructure. Dr. Martonosi is currently on leave from Princeton University, where she's a professor of computer science. Her recent research focuses on power-efficient wireless networks. She's also an elected member of the American Academy of Arts and Sciences, and a fellow of the Association for Computing Machinery and the Institute of Electrical and Electronics Engineers. As we celebrate NSFNet's 35th anniversary today, I would be remiss if I did not also acknowledge that this year also marks the National Science Foundation's 70th anniversary since its creation on May 10th, 1950. I want to congratulate NSF on this remarkable milestone and acknowledge their ongoing support and investments in funding science and engineering research here in the United States. With that, please welcome Dr. Martonosi.
Thanks so much, Anna, and it's wonderful to be here. It's really quite something to be a part of a celebration like this. As you mentioned, I lead the Computer and Information Science and Engineering Directorate at NSF, which is celebrating its 35th anniversary in 1986. So a wonderful and exciting time. When I give talks about NSF and CISE, I often use the analogy of planting trees, that research is about planting trees so that some generation in the future can have shade. And I think an extraordinary example of this is today being able to meet virtually using video conferencing because of the trees that were planted 10, 20, 30, and 35 years ago in the areas of high-speed networking, graphics processing, and so forth. And so in many ways, what I'd like to do today is to talk about what are the trees that we have planted and how are we cultivating them in order to have equally impressive and exciting and important impacts in the future. I won't look back too much because you guys have done such a wonderful job of sort of conjuring up those memories for us. The key thing from this slide is the degree to which NSF continues to see its role in supporting evolutions and revolutions to empower researchers and empower educators to come together to communicate and to share important computing ideas nationally and worldwide. As we all know, today, science and society continue to be deeply transformed by compute and data. Nearly every field we can think about is transitioning from a sort of data poor to a data-rich world mode, which has all kinds of implications. It has implications for the scientific process that's evolved to essentially deeply incorporate compute and data as part of science. But it's also had implications on almost every aspect of our society and economy as well. So what we're seeing are extreme scales, a data-driven sort of stance, and data compute intensive operations throughout. When I talk about the CISE Directorate and the research that we support, I tend to view it in terms of three big inflection points and then a set of technical themes or organizational umbrellas that pull together many important trends around those inflection points. And I'll talk about them very briefly here today. I could give a whole talk just about these three. So in a nutshell, the first one I refer to as CISE in a post-Moore world and the seismic shift. And this refers to the end of Moore's law and Dennard's scaling, or at least their slowing, which is impacting all aspects of computing. So it's easy to think, yes, it's impacting the transistors and the circuits. Really, it's impacting the full stack, hardware and software. And as we embrace things like heterogeneous accelerators in our compute devices to deal with some of the hardware challenges, we're changing the software model in ways that affect security, reliability as well. That in turn affects our curriculum. So there's huge opportunities to reinvent around that inflection point and the themes that it has generated. The second technical theme for the computing world is around AI and its transcendence. And I think many of us here today are well aware of the fact that AI is almost as electronic computing itself. What is different about AI today compared to its dawn in the 50s is that now it is able to draw this from all of computing inflection points. So it's improvements in algorithms, yes, but it's also the availability and suitability of large-scale data and the availability and suitability of large-scale compute systems on which to compute, on which to train. So one aspect of AI is its successful confluence across these different topic areas. Another aspect is its impact. It's broadly fueling advances and implications across our field and across society. And understanding that interplay is truly about a transcendent kind of topic, not simply sort of a focused subtopic the way AI might once have been viewed. The third inflection point that engenders a set of themes for me is about the degree to which CISE has shifted from being a technical field to being a truly socio-technical field. So more so than ever, our field is shaped by being sort of integrated between our technologies and on how humans use them and are shaped by them. And it's this socio-technical frontier, which means different things to different people, but has huge impact. So this is connectivity and the digital divide. This is human-computer interfaces. This is accessible technology. There's a broad set of opportunities where we have the chance to re-examine the technologies we're developing, their implications on society, and how to innovate there in the most productive and useful ways. And I think some of the previous speakers sort of alluded to that. It's certainly very much on the minds of us at NSF and the research community that we represent and fund. So one question is sort of how do you advance on those themes? If I've articulated a set of inflection points and themes, how do we move forward on them? There's different elements to that: budget, people, partnerships, and so forth. The one I would focus on today, sort of motivated by this event that we're all celebrating, I'm going to focus on infrastructure. And in particular, I view infrastructure as a key aspect of how to enable scientists to do their best science, much like putting out a table of art supplies and seeing what a set of artists can come up with. Briefly, here's a sketch of what our directorate and NSF infrastructure programs look like. So these are programs that people can propose to. They range from, on the left-hand side of the x-axis, programs designed to help support an individual or a single institution, up to programs that are designed to support truly national needs across a full research community. They also vary in size. One of the things that I will note for the researchers out there in the audience is that we have a mid-scale research infrastructure solicitation in 2 different sizes that's now live. And those are some of NSF's although the name is mid-scale, those are fairly sizable investments from $6 million to $100 million per award, with the idea being to sort of cultivate what is next for infrastructure, where infrastructure is not just hardware, but it's also software, data, and people. And I think given where we are as a research community, we can see the value of infrastructural software on our advances. We can see very clearly the value of large-scale data repositories as well. And so thinking broadly about what infrastructure is and how it can cultivate new research ideas is really important to NSF's mission. So as I said, there's actually 2 scales. Mid-scale research infrastructure 1 is $6 to $20 million per award. Mid-scale 2 is $20 to $100 million, and you can see the deadlines there. What I'm going to do over the next few slides is paint a picture of different infrastructural investments that NSF has made in recent years, and then I'll use that to pull together towards a vision of a national research cloud or a national research computing resource. And so one example of the set of sort of cyber infrastructure that we at NSF and within the CISE Directorate invest in is this map of our OAC, or Office of Advanced Cyber Infrastructure's advanced systems and services. And you can see the highlighted arrangements that represent everything from leadership class computing, such as Frontera, the most capable supercomputer on a US academic campus right now, to a range of other capacity systems and different types of innovative prototypes as well. Frontera, we are incredibly proud of NSF's role and Frontera's role over the past year in the COVID-19 HPC consortium. Over 30% of the compute cycles and over 40% of the projects that came in through that public-private partnership to advance the world's understanding of COVID-19 and its impacts. A very large fraction of those went on to NSF systems to be resourced for their science. So that's one map. You can look at other types of NSF-funded resources. So for example, within the CISE directorate, we are currently piloting something called Cloud Bank, which you can see at the top of this slide here, that's intended to explore models for providing researchers access to commercial cloud services. Cloud Bank is now an integrated part of our CISE core research solicitation. So essentially any researcher proposing to the core research programs of CISE has the opportunity to ask for a budget of cloud cycles as part of that. They are stored in the quote-unquote Cloud Bank, and Cloud Bank acts as an intermediary to send compute jobs off to commercial cloud providers that partner with us. That's in a pilot mode, but scaling up across programs and across numbers of researchers now. And you can check out cloudbank.org if you're curious for more information there. As the previous speaker mentioned, we're also excited about ECAS, which is about using commercial cloud providers in partnership with different scientific platforms and facilities as part of leveraging clouds for high performance computing and for scientific endeavors as well. And then finally, CC Star, which was on that previous infrastructure map, is about clouds and campus computing to federate campus cyber infrastructure and to integrate cloud services and expertise into campus cyber infrastructure. But it goes on from there. So there's also the Open Science Grid, which is intended to recognize that, as I said, infrastructure is not just the compute cycles, but it's also the data. And so the idea of Open Science Grid is to form a serious compute and data analysis platform that couples into large-scale scientific facilities, like the Large Hadron Collider and like the IceCube neutrino experiments. So these are cases where the resources come from the community, are organized by Open Science Grid, and then are governed by a consortium that partners these together. And it also integrates resources funded by the CC Star program that I mentioned on the previous slide. So hopefully what I'm doing in this step-by-step progression is showing you the degree of different resources that NSF funds and the way that we are starting and continuing to advance this idea of confederating those resources together. So what's next? A lot of what I've talked about so far was about sort of HPC, cloud, and data. Let's switch gears a little bit and talk about advanced wireless. If you're a researcher and you're interested in testing out your algorithms, your protocols at scale, then the ability to couple into advanced wireless test beds, the ability for your students to learn in that hands-on way is key. So Power, the Platforms for Advanced Wireless Research, is a major public-private partnership with roughly 36 companies and associations donating in-kind and cash resources towards the standing up of a set of Power test beds nationally that you can see on this map. So this lets people do things like study drone systems, study different types of next-G systems, and so on. In addition to the blue and orange elements that you can see on the map, we're also thrilled that in our most recent Power solicitation, we focused it around the motivating theme of affordable rural broadband. And about a little less than a year ago, we narrowed down to 2 finalists at the University of Nebraska and at Iowa State University. And we're currently giving them 1 year of seed funding in which to do what we call a bake-off. So basically let them advance their ideas further in the hopes that we will be able to fund one or both of them in the coming year to add to this power testbed the notion of novel techniques for affordable rural broadband. So now you can start to see a picture that there's sort of pockets of very deep compute and data resources. There are things like the fabric network infrastructure that interconnects resources, and there are wireless test beds and so forth as well. And what we want to sort of look forward towards is a vision where these things are confederated so that I, as a researcher, can come in and do work that actually confederates and combines different resources together as seamlessly as possible. So to mix wireless and cloud together in novel ways, for example. So this vision actually is something that's been talked about in public circles quite a bit. Here's one quote, but there are many. This is Eric Schmidt in his testimony about a year ago to the House Science Committee, talking about how notion of a national research cloud could be well supported, could be an appropriate vision for us. And in this particular quote, he mentioned our Cloud Bank pilot as a part of that. But as I've shown in this step-by-step set of slides, clearly we see ourselves as converging with much more than Cloud Bank. It's a much broader set of resources. The goal is to scale from Cloud Bank's pilot and from other extreme digital capabilities that I've shown you to this full national capacity. And the other goal, the far more important goal, is to say we have these resources, we fund them as a nation, and it's our goal to democratize access to this rich and diverse set of NSF-funded and other research resources in order for those to be Lego blocks, to be the art supplies that we put out on the table so the next generation of researchers can come up with truly novel and important and effective ways of moving us forward in these different topic areas. So how do we move towards that? So right now, we have something that looks like the beginnings of this. You could imagine a set of NSF projects or PIs over on the left, and they flow through intermediaries and onto some set of components. So first of all, commercial cloud resources. You saw that with Cloud Bank and ECAS in my slides a couple slides ago. Second of all, NSF-funded specialized resources, which include advanced computing like Frontera, wireless testbeds like Power, and other techniques like experimental cloud services such as Future Cloud. And then the third element are community-donated resources, which might be cycles or data to sort of fill out this research computing resource to go beyond just cycles and into a sort of an acknowledgement of the degree to which rich data sources, rich software and so forth also play into this. I want to end this part of my talk by hearkening back to what you've heard through essentially every speaker today, which is the degree of experimental possibilities that these ideas have. So we could sort of stand something up today, but we see tremendous research opportunities in treating this national cloud, this computing research resource, as itself a research platform to understand things like programmability, resource discovery, and portability across these confederated resources. So to make the testbed, to make the research cloud itself a place for innovation and for research. And so with that, I'm happy to be here. I'm happy to see sort of this chance to look back at the amazing impact that NSFNet had. And I'm also happy to have gotten the chance to paint a little bit of a picture of looking forward about how do we advance on these scalable resources that we fund? How do we confederate resources and platforms and data together in a way that is effective in allowing for research and science and societal impact to converge in key ways? How do we democratize access so that every student, every researcher across the country has the same ability to try out their ideas at scale? And thereby, how do we promote the geography of innovation that's so important to NSF, that's so important to our nation going forward? And so with that, thanks very much.
Thank you so much, Margaret.